Okay, this video is to show you how to do the second level of the DC single node pair single loop tutorial. So I'm already in the level menu. As before, the first thing you would have to do would be to view the second section of the tutorial on the website, and so you would have to click this button. I've already skipped that, but normally you would be required to do that before you can actually access the exercises. And again, I would also recommend that you look at some examples. And that will help you understand what you need to do. But once again, you cannot enter equations with two equal signs when you're actually doing the exercise. So don't try to write it exactly this way. You would do these things separately. Okay, so once again, you won't have the choice of which problem type to work, but I do that, so I'm going to show you each problem type in turn. Okay, so here's the first problem type, and as always, I need to select the type of circuit analysis. Now this is not both single node pair and single loop, unlike the simpler problems on level 1, so I have to pick the right type. And I see it is a single loop, unless you also count the outer loop, I guess. But it is not a single node pair because I have 1, 2, 3 nodes, and that is not 2 nodes, as I would need to do that method. So if I try to do that, it's going to tell me I can't do it. Okay, so I have to do single loop analysis here. The next thing, of course, as always, is to select the type of equation. So clearly I want a voltage here, which appears across a branch or an element. So that's a branch voltage. So I select sought branch voltage here from the menu as to the type of equation. Having done that, as always, I get my palette here. And I'm going to select V0 equals. And now I could mentally compute the current and use this equation, but I'm going to instead use this voltage division formula. And I should point out, by the way, that you might think, well, I could use a Kvl equation to solve this problem. And indeed, you could do that. However, the program will actually not let you. So if you try to write a Kvl equation here, it's going to tell you, you don't need to do that, just write the sought voltage equation anyway, because it wants you to use the voltage divider formula so that you learn that formula. So it's actually not going to let you do that. So I'll pick this, and then V0, I'm going to use this voltage divider formula here, which is, of course, if I hover over it, it tells me what that's for. And so now I'm going to have 8 volts that gets divided among the 2 resistors. So the 2 in the denominator are the 7 and the 3 ohm. And of course, 8 volts divided by that total 10 ohms is going to be the current, which is going to be 0.8 amps. And then I multiply that times the resistor that has this sought voltage, which would be the 3 ohms. That's the voltage divider formula. But I always have to check carefully the polarity anytime I'm doing voltage or current division, or pretty much anything in circuits. I need to check polarity. And I notice here the plus side of the sought voltage is actually connected to the negative side of the source, and the minus side is connected to the plus side. So that means I'm going to need a minus sign here, otherwise the answer would be marked wrong. So now I can check that equation, and indeed it is correct. And that's all I need. It tells me I'm completed, basically. And so now it asks me to evaluate that, since that's not a number. And so I simply would do the computation there. That's 3 over 10, 0.3 times negative 8 would be negative 2.4. And that is the correct number. Okay, and as always, I can get a detailed explanation if I like, which will explain the polarity issue and so forth in more detail. So it's oftentimes a good idea, if you were just unsure about the answer, to look at those detailed explanations so that you can become more confident in your work. Okay, so the second level, this is going to be a little bit different, and now I actually have a sought current rather than a sought voltage. So it's still a single loop circuit, so I have to pick that method. And now the equation type here, well, in this case, it actually is going to allow me to write a Kvl equation, because using the voltage divider formula wouldn't make much sense when I want a sought current. It would just not really help. So it's going to allow me to write a Kvl equation, and it gives you a warning here. It says don't combine elements in series when writing these equations. In fact, the first time you do this, it would actually give you a pop-up explaining that in more detail here, which it didn't show because I've already done that. But so I need basically to have a separate equation term for each circuit element. So if I tried to combine the 1 ohm and the 3 ohm resistor, which of course is legal to do, but the program is not going to let you do that because it wants to have a separate term for each thing. Eventually we may change it so that it'll accept that, but right now it doesn't. So I need a term for each resistor, and then I need a term for the voltage source, which is just going to be a voltage drop, and then the sum of those will equal 0. So I have that equal to 0. Now, the current number here is always current 1 since it's a single loop. And the n stands for integer. So basically that's going to be an integer. In this case, it'll be 1. And as you're entering these things, I would strongly recommend you use the tab key to go between these fields. That'll make it much faster for you to actually enter the values that you need to enter. So I'm going to put a 1 here. I'm going to press tab to go to the next field. And let's do the 3 ohm first. And then 1 ohm, I1 rather, times 1 ohm. And now here, I have to think about this because there's a polarity issue. So I'm adding voltage drops actually as I travel around in the direction of the mesh current. And so these were automatically positive because the current flows from high to low voltage through a resistor. But this one could be positive or negative. So I see here this is actually voltage drop because I'm going from +7 to 0, say, or well, in any case, it goes down by 7 volts. So that's going to be a plus sign since I'm adding voltage drops. So I'll put in my 7 volts. Now, if you prefer to add voltage rises, you can do that. You would just make every term negative. So I put a minus sign here, a minus sign here, and then a minus sign here. That will also be accepted. And in fact, if you want to put some of the terms on the right-hand side of the equation and some on the left-hand, or for example, if I wanted to move this over there and this over there, I can do that. Any algebraically valid form of the equation will be accepted if it's correct. People often tell me, oh, it won't accept my version of the equation. And unfortunately, the reason it's not accepting it is because their version of the equation is wrong. So if it's not accepting it, it's not because you just wrote it a different way, it's because you wrote it incorrectly. Now, the only exception to that, as I said, is if you were to combine these two terms. It doesn't let you do that, so that's the only restriction of the program. Okay, so I'm going to check that, and it marks it correct. Now I also need a SOT variable equation, and I'm trying to calculate a current here, so I will select SOT branch current. And my I0 here, I can express it right in terms of that I1. Notice it's going actually in the same direction. Both are clockwise, and so it's going to be a plus I1 here. And so I'll check that, and that is indeed correct. I'm now done, so I just click no more equations. And now it asks me to solve those equations because, of course, I don't have an answer yet. So first of all, I have to solve this equation for I1. So I would just combine those. That's 4I1 plus 7. So this is going to be -7/4 or -1.75. And that's correct. And then I now need to use my SOT variable equation. And I can move this, of course, around to see. With this value, I need to basically say, well, it's the same thing. So in this case, I just enter the same number. In other cases, it could be different. So I check that, and it's correct. And now I'm done. I can also view a detailed explanation, which I'll show you here. In this case, it's actually showing you the voltage drops around this dashed loop here, dashed in red. And it's actually color coding the equation, the terms in the Kvl equation to match. So for example, the red term here is the voltage drop across the 3 ohm resistor, and the plus minus signs illustrate that that's a voltage drop while moving clockwise. And the magenta term is the 7 volt drop here, and then the blue term is the drop across the 1 ohm resistor. If you want a more detailed explanation of that, especially about the polarities, then there's a button here to explain that, and it'll give you a very detailed explanation to help you understand that. And then we're done with that. So now we'll go on to third problem type. And again, it is a good idea to look at examples here, but in this case I'm going to skip that. Now this is not a single loop circuit. As you can see, it actually has 3 meshes, so or 4 if you count the outer mesh. And it is, however, a single node pair because there's only 2 nodes. So I have to select that type of analysis. And again, the form here is a little bit messed up because of my screen capture program. But okay, so now I can select a SOT branch current because that's what I need to calculate. And so I0 here, I'm going to use basically the current division formula or some version of that. So I could do it in terms of reciprocals of ohms, or I could do it in terms of Siemens. Remember that a Siemens, a capital S, is a unit that's the reciprocal of an ohm. I'm going to choose this particular term in this case, just my own personal preference, but you can use either one. So here we have the 5 amps, and then again using the tab key here, this is going to be the resistor in question, so it's going to be 1 over 4 ohms, or that would also be 0.25 Siemens if I were using the other type of term. And then 1 over 4 plus 1 over 1 plus 1 over 8. So I'm adding basically, I have the conductance of the term in question divided by the sum of the 3 conductances is what that is, which you could also express using this term if you like. And that is correct, and it's going to plot it for you that way. And that's all the equations I need. So now it just asks me to enter the numerical value, so I would have to compute that using my calculator. And that would actually work out to be 0.909 amperes. So I check that, and that is correct. And once again, I can see a detailed explanation. If I like, it's going to show me how to do it in terms of the different types of things, which is good to become familiar with. So it would be actually helpful probably to read that. Okay, the next type of problem. This is one now that again is a single node pair type of problem. So I have to select that method. If I select the other one, it's going to tell me I can't do that because it has more than one mesh, more than one inner mesh. And now I need to calculate a voltage, so I'm going to select a sought branch voltage because that voltage is across one branch, the 7 ohm resistor. And now I'm going to express that. I could express it as a number, but it's easier here probably to do it in terms of the node voltage. And notice it's added now a reference node here, and it's denoted this node and automatically numbered for us as node 1. So V0 is related obviously to V1. That's the only voltage in the circuit. But notice that the V0 has a plus sign on the reference node and a minus sign on V1, so that requires a minus sign here in order to be correct. So when I check that, that is correct. And now I also need a Kcl equation in this case, or Kirchhoff current law equation. So that means I'm going to add the node currents leaving a node. And so that's a new type of equation we're going to be using here. And again, it reminds me, don't combine elements in parallel when I'm writing a Kcl equation, just as you don't want to combine elements in series mentally when you're writing a Kvl equation. Okay, so that means I'm going to need a separate equation for the current leaving each, leaving node 1, say, through each resistor. So that needs 2 of those, and then one for the current source, and then that'll equal 0. And again, it doesn't matter how you arrange these terms as long as it's algebraically correct. But I'm just going to do it this way for simplicity. So if I'm adding the currents leaving node 1, that would be V1 over 7. And again, I use the tab key to go quickly. V1 over 6 would be the current leaving through the 6 ohm resistor, and then the current leaving through the 2 amp source, well, that's actually going to be minus 2 amps because the current is in fact entering through the 2 amp source, so it has to be a minus sign there. And again, if you want to do currents entering, you just change all the signs. That'll still be correct. Okay, that's all the equations, and so now I just need to evaluate the equations, first by solving for V1, so I just use simple algebra there, and add a 7th to a 6th, over a common denominator, or just using my calculator. And so that'll work out to be 6.46 volts in this case. And then I have to use the sought variable equation and just basically take the negative of that number. And that's done. And once again, we can get a detailed solution. In this case, it's showing you the currents leaving that node as these little colored arrows, and then it's color coding each term in the equation to match. So you see this is the red term is the current leaving through the 7 ohm, magenta is through the 6 ohm, and the blue is current leaving through the 2 amp source. And this explains this in more detail. And also there was an option there to get a detailed explanation of that. That button's gone now, but it was there. Okay, the next problem type, let's do one of those to be complete. And this looks like a little bit more complicated circuit, but in fact it is still 2 nodes if you notice. There's one node here and then another node here. So that would be a single node pair. And now it's coloring that for us. It's applied the reference node automatically and numbered node V1, since there's only really, well, I mean you could do it the other way, but this is how it's doing it. And now I need a power dissipated in the 8 ohm source. So that's a sought branch power. So I will select that type of term. Again, it's reminding me about the 2 different palettes of terms for power, so I want to keep that in mind. I may need things on the second palette, okay, which is why that's flashing at me. Okay, so here, let's see, I want the power there. So I think the easiest thing would probably be to, not any of these terms, but I think I'm going to go over here and pick V1 squared over that resistor. So remember the N stands for integers, and so that would be the node voltage index here. And then this would be divided by 8 ohms, and that would be the correct equation for the power dissipated in that resistor in terms of V1. So that is correct, but I also need a Kcl equation so that I can actually evaluate V1, right? Otherwise I wouldn't know what to put in for V1. So then I have to pick a Kcl equation to sum the node currents, leaving a node, and again, I'm not allowed to combine elements in parallel. So in this case, I would need 1, 2, 3 terms for resistors, and then 1 term for a source, because there's 3 resistors and a source here. All that's equal to 0, and I'll have V1 over 8, and V1 over 3, and V1 over 6 for the current going this way, and this way, and this way, respectively. And then the current going out of node 1 would be 3 amps with a plus sign here, because that current source does in fact leave V1. So if I check that, that is correct. And that's all the equations I need. So now I would have to solve, again, that first equation for V1, just using simple algebra, combining these 3 terms, moving this to the right, and then solving for V1. So that would work out to be negative 4.8 volts. Then I just use my calculator to square that and divide by 8. And when I do that, that would work out to 2.88 watts. And that is the correct answer. Okay, and then once again, we can get a detailed explanation if we like, again using those current arrows to help you visualize the currents leaving that node 1. Okay, and again, you can get this detailed explanation if you need that. And there's the node coloring to help you visualize the 2 nodes again. Okay, problem type 6. Now this is once again a single loop circuit, so I have to pick that type of analysis. And now I want a power dissipated in the 4 ohm resistor, so I pick a solid branch power. And it once again reminds me of those 2 terms of palettes that I might need, or 2 palettes of terms I mean. So that would be equal to this. In this case, the term is right here, so it's going to be I1 squared times 4 ohms. That's probably the easiest form to use. Some of these others might be possible as well. I could always put a numerical answer in here if I want to do it that way, and then I wouldn't need to do any further work. So, you know, that's fine if you like to do it that way. I'm just going to do it this way right now. Okay, and then I will also need a Kvl equation for the mesh. So once again, don't combine those things in series, so I need a separate term for each resistor, and then a term for the voltage source. 3 elements means 3 terms, and that's going to sum to 0 by KVL. So this would be I1 times 7 ohms, plus I1 times 4 ohms. And I'm adding the voltage drops as I go around clockwise in the direction of I1. And so in that direction, this is actually not a voltage drop, it's a voltage rise by 4 volts, because this is the negative and this is the positive. This is the higher voltage here. So I need a minus sign in that equation. And that would be minus 4 volts. When I check that, that is correct. And now I just need to, again, solve the equations, as always, for I1 first. So I'd put the 4 volts on the right-hand side, and I'd have basically 4/11ths would be the answer, or 0.364. But again, don't try to enter a fraction. It will not accept fractions. So you have to enter it as a decimal using your calculator. And then here, you would just plug that number back into here, square it, multiply by 4. And when you do that on your calculator, you'll get 0.529 watts. And that's the correct answer. Okay, and then once again, you can get a detailed solution, and in this case showing the voltage drop on each element, showing the structure of the KVL equation, or detailed explanation here. Now the 7th problem type. Now again, we're looking for the power, but this time it's the power delivered by the 6-volt source. It is a single loop circuit. It's not a single node pair because I got 1, 2, 3, 4 nodes, so I can't use that. So I'll use single loop. And then, since I want a power of a source, I will, again, look for a SOT branch power. And in this case, I want the power supplied by that source, and so it would be the I1 times the value of the source. It's always I times V, so it would be I1 times 6. But I do have to check that current is actually going into the source. That's the passive sign convention, and for power supply, I don't want active sign convention, so I need to use a minus sign there. Okay, so that's correct. And then the other thing I need, of course, is my Kvl equation. Going around the inner mesh here. So again, I don't want to combine those things in series mentally, so I'd have to have 3 terms, not 1, for the resistors, plus voltage equals 0. And that's going to be I1 times 2, for example, times I1 times 7, plus I1 times 6. Those are the 3 resistors. And then as I'm going around clockwise, adding those voltage drops, this is actually going to be a voltage drop this time because I'm going from plus to minus. So that will be a plus 6 as opposed to a minus 6. Okay, if I put in a minus, just to show you, it will tell me it's wrong. Okay, and unfortunately that was too many mistakes on this problem because it's a very simple problem. So you will have to now work a new problem. Okay, I will continue it nonetheless, although I won't get credit for it. And that's correct. And then I'm done with equations. Now I have to solve. And solving for I1 here, just again with simple algebra, that's going to be 9/15, so it'd be negative 6/15. I'm sorry, negative 6/15, which is minus 0.4. And then I put in, again, the value here, just taking negative I1 times 6 is going to give me a positive number of 2.4. So that is correct. But I didn't get credit because I made the mistake basically on the crucial sign error. But I can, of course, still always get the explanation here. Okay, and then for the last problem type, then I'm going to choose a single node pair analysis here because this is a single pair of nodes, but it's actually 3 interior meshes. So now I want a power supplied by a current source. So again, that'll be a sought branch power because it's asking for the power supplied by the 8 amp source. So that's going to equal what? Well, in this case, it would be this term would be the appropriate one, which would be a V1 times the current of that source, which is 8 amps. And now I've got to always check the sign convention here. So if I'm looking for the power supplied, well, that's putting current into basically the ground, which means that this has to have a minus sign. And so I have to use the active sign convention there. Okay, then I need to write a Kcl equation, as usual. And so I need 3 terms for each of the 3 resistors and a current source term. I don't need these dependent source terms, and those are equal to 0. And so I'm going to have V1 over 2 and V1 over 5 ohms and V1 over 7 ohms. That represents the current leaving V1 through each of those, the 2 ohm resistor, through the 5 ohm resistor, through the 7 ohm resistor. And then finally the current leaving the through the 8 amp source is just 8 amps in this case because the current is in fact leaving node 1, so that will be a plus sign. Check that, and that's good. And then I solve for V1 here, which in this case works out to be negative 9.49. And finally, I plug that value in to this equation, and that will give me 75.9 watts. Have to be accurate within about plus or minus 1%. And that's done. And once again, I could look at the detailed explanation if I need that. And again, I would be completed without making that mistake, but you can always come back and work additional problems.